Hi everyone. In this lecture, I'll be introducing conditional probability. In a later lecture, I'll be talking about more advanced topics in conditional probability, such as Bayes' rule. So to start out, let me give you an example. Suppose since Malloy College was founded in 1955, there were 20,000 scheduled class days, and 100 of these days were canceled due to snow. So if we were to actually go under the assumption that we're randomly selecting one of these 20,000 days, with each one equally likely to be chosen, then we would say that the probability that we select one of the days that was canceled would just be 100 out of 20,000. That's the number of canceled days divided by the total number of scheduled days, which would be 0.5%. Another way of looking at this is there were 20,000 trials or 20,000 opportunities for there to be a snow day, and 100 of them were canceled due to snow. So we would say the probability that it would be canceled from that standpoint would be, again, 0.5%. So regardless of whether you're viewing this experiment as selecting one of these 20,000 scheduled class days at random, or viewing this as 20,000 trials where you had an opportunity for snow to occur, the probability would be of getting a canceled class day due to snow would be 100 over 20,000. That's the number of days that were canceled due to snow over the total number of class days. Okay, so let's now actually consider conditional probability. So here we're actually giving the information that it's May. And we want to determine the conditional probability that it snows. So obviously if we're in May, we would expect the conditional probability of snow to be less, a lot less. In fact, we'd expect it to be close to zero. And that's exactly what we have here. We have 0 days were canceled due to snow in May. So when we're considering snow days, we're only considering the ones that appear in May. And we're going to be dividing only by the number of days that were scheduled for May. It doesn't make sense to talk about all of the scheduled class days if we're given that we're in May. So here it would just be 0 over 1,300, which is 0 or 0%. On the other hand, if we're talking about February, we would expect the probability to be more than that 0.5%. Right? Because the 0.5% represents the average over all of the days, including days that are in February, including days that are in May, and all the other months. So here we could see that the probability would be 35, that's the number of snow days in February, over the total number of scheduled class days in February, which is 1,400. So that is 2.5%, which is 5 times as high as the probability of snow day if you're not given the month. So now we could consider one more conditional probability, and that's that Hindi was spoken somewhere that day. Now in this case, Hindi would be spoken every day somewhere, every day of those 20,000 scheduled class days. So this is really not going to affect the probability at all. We would say, okay, how many of the days were snow days where when Hindi was also spoken somewhere, divided by the total number of days, the total number of class days, that is, where Hindi was spoken. So we would again get the same probability of 100 over 20,000, which is that 0.5%. So we could see in the 3 cases, in one case, the conditional probability went down. In the other case, that was when we were in May. In the other case, it went up when we were in February from 0.5% to 2.5%. And in this last case, where the information we were given was independent, really it gave us no extra insight as to whether we were more likely to have a snow day or not. It remained the same at 0.5%. Okay, so this example was really to provide motivation for our conditional probability definition. First, let me just introduce some notation here. We have P, rather than just having P of E, we have P of E vertical bar F to denote the probability of E, or the conditional probability that E occurs, or that some outcome in E occurs presupposing that we know with certainty that an outcome in F did. So considering this snow day example, we can model this as a set of the positive integers from 1 to 20,000. That is, we can model the sample space as just being the set of day numbers corresponding to each class day we've had, with 1 being the first one, 2 being the second one, 3 being the third one, since the school was founded in 1955. And then if we wanted to consider the event, which would be a subset of the canceled days of classes due to snow, that would actually be the day numbers that it snowed. So for instance, if it snowed on the third day, the third day of classes that since Malloy was founded, then 3 would be in this set. So if we wanted the probability of having a day that was canceled due to snow, or the probability of this event E, all we would do would be to take the number of days, right? So the size of the set E, the number of days that it snowed, which would be 1,000, and divide that by the total number of days, which would be the size of S, which is the 20,000, right? And then we would get our 0.5%. Now, if we wanted to consider the conditional probability that it snowed, given that we were in a day in May, E would still be the same, right? E would still be the set of canceled days of classes due to snow, right? That would still have a size of 1,000. But now, instead of actually considering S, which would be the set of all possible days, all possible scheduled class days, we would only be considering the subset of scheduled class days in May. So if there were 1,300 days, we would be considering a set of size 1,300. And the set F would be the day numbers that corresponded to class days in May. So if, let's say, the first day that it was actually in May was, the first class day that was in May was, let's say, I don't know, like 200, right? So then 200, let's say, is the 1st of May, and that was a class day, and 201 was the second day in May, and 202 was the third day in May. These would be all those numbers that were in F. But when we're considering the conditional probability that it snowed, or we had a snow day, given that we were in May, we don't consider all of the days that were canceled due to snow. We only consider the days that were canceled due to snow that were in May. So we're looking for days that are both in E and F, and that corresponds to the intersection of the two sets. So whereas 3 might be a snow day that's in E, 3 might not be a day in F, right? So 3 might be a day, let's say, in November or December, and that wouldn't be in F. So that would not be considered in this E intersect F, right? So we would be taking the size of E intersect F, and if we had the situation where none of the snow days were actually in May, then E intersect F would be the empty set, and the size of the empty set is 0. And again, here we're dividing by the total number of days in May, not the total number of days. So to get the probability, we would be doing the size of E intersect F over the size of F, which would be 0 over 1,300, or 0, right? So this would be the probability that we had a snow day, or we had a day that was canceled due to snow, given that we're in May. Right now, if instead F were the set of scheduled class days in February, it would be the same thing, except F would be a different set. So F here, the size is 1,400, and here we would expect the intersection of E and F to not be empty. Here we would expect that there were class days with snow that were also in February. So if we're doing the probability that it snows, given that we were in February, we would take the number of days that that were both canceled due to snow and were in February. So again, the intersection, days that were in the intersection, day numbers that were in the intersection of these two sets, we would take the size of that, which we said by assumption was 35 because we said there were 35 snow days in February, and now divide by the total number of days in February, or the size of f, which we said was 1,400. And here we get our 2.5%. And finally, we could consider the case when we're talking about our f being information that wasn't very useful, which was just that Hindi was spoken that day. So we would expect that on all the days of all those 20,000 days, Hindi was spoken. So what that really means is that the size of f is 20,000. F is the same set as s. It's the set 1, 2, 3, all the way up to 20,000, all those positive integers. So if we take the intersection of if we take the intersection of the sets E and F, that's the same as the intersection of the sets E and S, since F is just equal to S. And since E is going to be a subset of S, meaning that E, if it's in E, it's going to be in S. S is going to include all the days in E. Then the intersection of these two sets is just going to be E itself, right? If it's in E, since E is a subset of S, it'll also be in S, so we know it's going to be in E and S. And clearly, if it's in E and S, then in particular, it's in E. So these two sets have the same elements, so they're the same. So now if we go and look at this again, we say the probability of E given F is going to be the size of E intersect F, which is just 1,000, right? Because we said it's really just the size of E, which is 1,000. And we're going to be dividing by the total number of days Hindi was spoken, which again, F is just going to be the set S. So we're just going to be dividing by 20,000, and we get the same 0.5%.